What is a DBS and how does it differ from a traditional base station? Walk into any modern telecom equipment room and you will likely see something that looks nothing like the base stations engineers worked with 15 years ago. The cabinets are smaller. The cabling is cleaner. The hardware is more modular. And the unit responsible for all of that change is the distributed base station, or DBS. To understand what the DBS is and why it matters, you first need to understand what came before it, and why that older architecture eventually ran out of road. The traditional base station, how it worked. The traditional base transceiver station, or BTS, was a self-contained unit. Everything it needed to function lived in one place, usually a large cabinet or a dedicated equipment room at the base of a tower. The radio units, the baseband processing hardware, the power management systems, the transmission interfaces, all of it was packed into a single integrated system. From that cabinet, thick coaxial feeder cables ran up the tower to the antennas mounted at the top. These cables were the physical link between the radio hardware in the cabinet and the antennas doing the actual transmitting and receiving in the air. This architecture worked. For years it worked well enough. But it carried a set of problems that became increasingly difficult to ignore as mobile networks grew in scale and complexity. The feeder cables were a constant source of inefficiency. A coaxial cable loses signal power over distance, and on a tall tower those losses were significant. By the time the signal traveled from the radio unit in the cabinet to the antenna at the top of the mast, a meaningful portion of the transmit power had already been wasted as heat in the cable. Engineers compensated by increasing transmit power, which meant more energy consumption and more heat generated in the equipment room. The cabinet itself was large and heavy. It required a dedicated equipment room with controlled temperature, stable power, and physical security. In urban environments where space is expensive and landlord negotiations are complicated, fitting a traditional BTS into a viable site was often a significant challenge. Maintenance was also complex. Because all the components were integrated into a single system, a fault in one part often meant taking the whole unit offline. Upgrading the radio hardware to support a new frequency band meant a major hardware replacement project, not a simple swap. These limitations did not break the traditional BTS model, but they created a strong incentive to find a better way. The distributed base station was that better way. What is a distributed base station? The distributed base station is a base station architecture that separates the baseband processing functions from the radio functions and physically distributes them across two distinct units connected by a high-speed digital link. Instead of everything living in one cabinet, the DBS splits the work. The baseband unit, or BBU, sits in the equipment room and handles all the digital processing, protocol management, resource scheduling, data routing, and system management. The remote radio unit, or RRU, is mounted at the top of the tower, directly at the antenna, and handles all the radio frequency functions: signal amplification, modulation, demodulation, and transmission. These two units communicate over fiber optic or Ethernet cable running down the tower, using a standardized interface called CPRI, the Common Public Radio Interface. This cable is lightweight, thin, and carries digital data rather than radio frequency signals, which means it does not suffer from the signal loss problems that plagued the old coaxial feeder cables. The result is a cleaner, more efficient, more flexible system that solves most of the problems the traditional BTS created. If you like this video, please subscribe. Now we will talk about the main components of the DBS. Understanding the DBS means understanding each of its key components and how they work together. The BBU, Baseband Unit. The BBU is the brain of the DBS. It sits in the equipment room or cabinet at the base of the tower and handles all digital baseband processing. This includes managing the air interface protocols, scheduling radio resources for connected devices, processing incoming and outgoing data streams, and communicating with the core network. The BBU connects to the wider network through SFP ports, small form-factor pluggable interfaces. An SFP is a compact, hot-swappable transceiver module that plugs into a port on the BBU and provides a physical connection for fiber optic or Ethernet transmission. SFP modules come in different types depending on the transmission medium and distance required. A short-range SFP might connect the BBU to a nearby transmission node over a few meters of fiber. A long-range SFP might carry traffic over tens of kilometers to a distant aggregation point. The SFP interface is one of the details that makes the BBU a genuinely flexible piece of hardware. By swapping SFP modules, engineers can adapt the BBU's connectivity to whatever transmission infrastructure is available at the site, without changing the BBU itself. This modularity reduces costs and simplifies deployment across diverse site environments. The RTN, Radio Transmission Node. Between the BBU and the core network sits the RTN, the Radio Transmission Node. This is the equipment responsible for carrying the site's traffic over microwave links or other backhaul connections back to the operator's core network. Without the RTN, the BBU has nowhere to send the data it processes. The RTN connects to the BBU via Ethernet, creating a local site network that links the baseband processing to the backhaul transmission in a clean and manageable way. In modern DBS deployments, the BBU and RTN often sit side by side in the same cabinet or equipment room, connected by a short Ethernet patch cable, with the RTN then managing the microwave or fiber link that carries traffic off-site. The RTN is a critical part of the DBS ecosystem because it determines how much traffic the site can carry to and from the core network. A well-configured RTN with sufficient capacity ensures that the radio performance of the RRU is never bottlenecked by the backhaul. A poorly sized or misconfigured RTN creates a choke point that limits the site's real-world performance regardless of how capable the radio hardware is. The RRU, Remote Radio Unit. The RRU is the radio hardware of the DBS. It sits at the top of the tower, mounted on the mast or the antenna frame, as close to the antenna as physically possible. It receives digital baseband signals from the BBU over the CPRI link, converts them into radio frequency signals through a process of digital to analog conversion and modulation, amplifies them using a power amplifier, and transmits them through the antenna. On the receive side, the RRU captures incoming radio signals from mobile devices, amplifies them through a low-noise amplifier to recover weak signals without adding significant noise, converts them from analog radio frequency back into digital baseband data through demodulation, and sends them down the CPRI link to the BBU. Each RRU has a defined number of TRX ports, transceiver ports, that determine how many simultaneous radio channels it can support. More TRX ports mean more capacity. A 2-port RRU can serve a basic cell. A 6 or 8-port RRU can support a high-capacity urban cell with much greater throughput. The Antenna Jumper Interface. The connection between the RRU and the antenna is made through a short RF jumper cable. This is a brief coaxial cable, typically no more than 1 to 3 meters long, that connects the RRU's antenna port directly to the antenna's feed input. This short jumper is one of the defining advantages of the DBS architecture. In the traditional BTS, the equivalent of this connection was a feeder cable running the full height of the tower, sometimes 30, 40, or 50 meters, with significant signal loss along the way. In the DBS, that entire length is replaced by a jumper measured in single-digit meters. The signal loss across a 3-meter jumper is negligible compared to the loss across a 40-meter feeder. The jumper also simplifies antenna maintenance. Because the connection point between the RRU and the antenna is right there at the top of the tower, engineers working at height can quickly disconnect and reconnect the antenna without dealing with long cable runs. The jumper is standardized, weatherproofed at both ends, and designed to be installed and replaced efficiently during tower climbs. How the DBS differs from the traditional BTS. The differences between the DBS and the traditional BTS go beyond hardware placement. They represent a fundamentally different philosophy of how a base station should be designed. In the traditional BTS, integration was the guiding principle. Everything in one box, everything managed as a single system. This made the unit self-contained but inflexible. Upgrading one component often meant upgrading the whole system. A fault in the radio hardware could take down the baseband processing at the same time. In the DBS, modularity is the guiding principle. The BBU and the RRU are independent units connected by a standard interface. This means they can be upgraded, replaced, or expanded independently. If a new frequency band needs to be added, engineers mount a new RRU on the tower and connect it to the existing BBU. The BBU does not change. If the baseband processing capacity needs to increase, engineers upgrade the BBU without touching the RRUs. This independence makes the DBS dramatically more adaptable over the life of the site. Advantages of the DBS. The advantages of the DBS over the traditional BTS are clear and well established across the industry. The most immediate advantage is reduced feeder loss. Moving the RRU to the top of the tower eliminates the long coaxial feeder cable run that caused significant signal loss in the traditional architecture. The full transmit power of the RRU reaches the antenna, improving coverage and allowing operators to serve the same area with lower power levels, which reduces energy consumption. The second advantage is installation flexibility. A BBU is a compact unit that can be installed in a small equipment room, a street cabinet, or even a shared facility with other operators. It does not need the large dedicated equipment room that a traditional BTS required. This opens up site options that were previously unavailable or too expensive, particularly in dense urban areas where space is at a premium. The third advantage is scalability. Adding capacity to a DBS site is straightforward. Mount an additional RRU, connect it to the BBU, configure the new radio channels, and the site capacity increases. In the traditional BTS architecture, adding capacity often meant a much more disruptive hardware upgrade. The fourth advantage is maintenance efficiency. Because the BBU and RRU are separate units, faults can be isolated and resolved without taking the entire site offline. An RRU fault at the top of the tower can often be resolved with a targeted tower climb and a unit swap, while the BBU continues operating normally in the equipment room below. Use cases for the DBS. The DBS architecture is suitable for almost every modern deployment scenario, but it is especially well matched to certain use cases. Dense urban deployments benefit from the DBS because the compact BBU can be installed in small street-level cabinets while multiple RRUs serve different sectors and frequency bands from positions high on buildings or rooftops. This allows operators to deliver high capacity in environments where physical space is constrained. Rural and wide area coverage deployments benefit because the elimination of feeder loss means that the full transmit power of the RRU reaches the antenna, extending coverage range compared to a traditional BTS with equivalent hardware specifications. Multi-operator shared sites benefit from the DBS because multiple operators can install their own BBUs in a shared equipment room while sharing the tower infrastructure above. Each operator's RRUs serve their own frequencies and customers independently while sharing the physical mast. Indoor coverage solutions also use a form of distributed radio architecture derived from the DBS concept, where small remote radio heads are placed throughout a building and connected back to a centralized baseband unit, delivering consistent mobile coverage in environments where outdoor signals cannot penetrate reliably. Why the DBS represents the right architecture for modern networks. The traditional BTS was built for a world where mobile networks were simpler, slower, and less demanding. As those networks grew into the multi-band, multi-technology, high-capacity infrastructure that billions of people depend on today, the limitations of the integrated architecture became impossible to work around. The DBS did not just solve those limitations. It created a platform flexible enough to absorb the changes that 4G, 5G, and whatever comes next will continue to bring. Its modular design, its efficient use of tower infrastructure, and its clean separation of baseband and radio functions make it the architecture that modern mobile networks are built on. For any engineer working in telecoms today, understanding the DBS is not optional. It is the foundation of almost everything you will work on in the field. Thanks for watching. If you like this kind of videos, please support us by subscribing. It goes a long way to help us keep making this kind of videos.